Hey everyone, we're going to get started with lecture one, part two. I'm going to finish what we would have talked about if we had class on Friday. And so I'm going to go ahead and share my screen so we can get started with all of this. First is I did this slide for one of my classes, but not the other one. So I'm going to go ahead and start with this one really quickly, just for those who didn't get this material. So, talking about muscle proprioception. First, we need to think about what is proprioception and how does this help during physical activity. Recall what you know about muscle spindles and GTOs. So, since we're not here to answer this together, we know that proprioception is that kinesthetic sense, that ability to know where our body is in space at all times, without having to look down and see where our hands and legs are. How is this important in physical activity and sport? Well, we can dribble a soccer ball while looking at the goal and also identifying where our teammates are and not having to think about our feet moving and running. Um, we can dribble a basketball, same thing with our hands and not have to look down and see. So we basically have this constant loop of kinesthetic feedback where we're constantly receiving information from our body to our brain about what our body is doing in space. So obviously pretty important in any physical activities that we do. And then we talk about the two most important muscle proprioceptors that we have, muscle spindles and GTOs. We know that muscle spindles are embedded inside the muscle belly. They're these interphysial fibers, and they respond to stretch or lengthening of a muscle. And so they'll activate anytime a muscle is under a lot of stretch force, and they will send that signal to the spinal cord. And then the motor neuron that comes back to the muscle will tell that muscle to contract, right? It's a protective mechanism to prevent any overstretching or potential tearing of that muscle. And so that's what our spindle does. Our GTO is an extraphysial fiber that exists in the musculotendinous junction and it responds to tension. So any tension or force placed on the body, especially unexpectedly, will send a signal to the spinal cord. That motor neuron comes back to that same muscle under tension and tells the body to relax, right? Again, a protective mechanism to prevent any not overstretching, but any potential tearing of a muscle with too much force. Um, but our body has learned over time that when we have force placed on our back, it's not always a threat to us, such as when we lift weights. We have these heavy implements on our body, and if our body was to do what its innate job is to relax under that pressure, then we would just collapse to the ground, right? But instead, our body has learned how to adapt to that force and we can override or inhibit the action of the GTO, called GTO inhibition. This is a learned response, though. This takes practice, it takes a lot of experience in order to inhibit that GTO. And what this does is it allows us to be stronger submaximally. So it increases our submaximal force production and potentially maximal force production when we can inhibit and override that GTO. Okay, so now on to a topic that we're all new to here is, well, maybe not if you've had it in XFIZ, the motor unit. So I mentioned this last class when we met, defined as the motor neuron itself and all the muscle fibers that it innervates. So the motor neuron dictates those fiber type properties, such as dictates if we're looking at a type 1 or a type 2 fiber. Um, just to kind of understand this diagram here, we're looking at three different motor units. So we have three motor neurons, and then we have several different fibers. Looks like three to four for each one. And within, so the blue motor neuron connects to the blue fibers, the red to the red fibers, the purple to the purple fibers. All those different fibers are acting, I guess they exist next to each other, but they won't all activate unless all three neurons are activated. Then that entire muscle group will activate. You probably are pretty familiar with how motor neurons work and how that action potential arrives at that motor neuron, activating every single fiber. We know that's called the all or none principle. So all the muscle fibers within one motor unit will activate. Let's talk about the innervation ratio. So this is something you may not be familiar with, but this is basically how many muscle fibers exist in a motor unit per one motor neuron. So if we have one motor neuron, how many muscle fibers is that connected to? Well, it depends on the muscle and the job of the muscle. So most muscles that are larger in size and produce more dynamic, gross type motor movements, they will more likely be of larger size, have a higher innervation ratio. So it could be one motor neuron to 500 muscle fibers. We would find these in like our gastrocnemius or our glutes or latissimus dorsi, large muscles that do produce a lot of gross movements. An innervation ratio that's smaller, so one motor neuron to like 5 muscle fibers, that could be something like the muscles that we find in our hand that produce very fine motor units, or sorry, fine motor patterns, fine motor skills, rather than a large gross motor unit. So that's our innervation ratio. It just kind of talks about that one motor neuron to how many muscle fibers and how we find them. There are different innervation ratios throughout the body, but on average, the average size is one motor neuron to about 100 muscle fibers. Let's talk about the size principle. So I know we're familiar with this Henneman size principle, this orderly recruitment of motor units based on size. We know we're going to recruit those smaller type 1 motor units first, followed by the larger type 2A, followed by those type 2X. First, just to preface, you see that X/B. Previous literature research used to refer to that type 2X fiber as a type 2B fiber, but it was renamed to a type 2X. So if you look at older research or see older diagrams, such as this one down here at the bottom, you see that it's that type 2B /X. So that's what that one is. But let's refer to the Henneman size principle in regards to threshold level. And so if we're talking about threshold, we're talking about millivolts. We're talking about how much force is needed to activate these different threshold motor units. So low threshold fibers, lower force capabilities, and are recruited before those high threshold motor units. Basically saying that we don't have to do a lot of or any strenuous activity, don't have to produce a lot of force, don't have to do anything very intense in order for those motor units to be activated, to be recruited. Low threshold, you can think of the resting membrane potential, so that -70 resting membrane potential, and then you think of that threshold level, which is usually about -55. Those low threshold motor units, those type 1s, usually exist around that -55 or so. Um, the higher threshold motor units exist a little bit more negative, could be anywhere from -60, -65, and take more effort, more force to activate. And so if you look at this other picture down here at the bottom, when we start doing any type of activity with lower force capabilities, we're recruiting those smaller motor units first. And we may not activate any of those larger motor units unless we start to do something really intense. Like I mentioned a second ago about resting membrane potential is that -70. Well, that's an average that they basically teach about all motor units, but they're all different because they all have different sizes and they all exist at kind of different levels throughout the muscle. And so some are more positive than others, such as our slow twitch fibers. So slow twitch more positive, which means they're easier to activate. We don't have to do much for those to be recruited. If we look here in this resting membrane potential of human skeletal muscle ranging from -65 to -90. So -90 is pretty considered higher threshold for motor unit activation because most of our resting membrane potential we know exists around -70. So if they're -90, then that threshold level is slightly above that, meaning it still takes a lot of work to activate those high threshold motor units. But let's talk about what happens if we don't ever activate those. So when we do low force producing activities, such as going on a walk or a light jog or cycling or lifting very light weights, we're activating those type 1 fibers and probably tapping into some of those type 2As, those smaller type 2s, if we're doing anything like faster sprints, plyometrics, playing a sport, doing any jumping, swinging, kicking activities, we're going to activate those smaller type 2s. But what if we never do anything to activate those really high threshold type 2s? What if we don't ever lift heavy or ever sprint or ever do anything very intense? What happens to those? Something called denervation. Denervation is the loss of the nerve supply to those type 2 fibers, which where if we lose that nerve supply, we can never activate them again. We also know they'll experience atrophy. And so they'll atrophy, which contributes to the loss in muscle fiber size. And so we don't only lose the size of our muscle, we lose the ability to ever really produce high amounts of force again, or any powerful type activities or really fast twitch movements. And so that's why it's important to activate those every once in a while. Do something really intense, do some lift heavy, sprint, play a sport, do something of high intensity to keep those type 2 fibers active so they can kind of stay active for the rest of our life. Critical thinking question here, basically saying, do you think we have the potential to recruit every single motor unit, type 1 to A to X, in each of our muscles during a maximal attempt like we see down here at the bottom doing back squat? So with that first question, it's basically just trying to understand, okay, if I'm doing back squat with really, really heavy weight, so a really heavy 1RM, am I recruiting every single muscle fiber in all my quadricep muscles in my gluteus maximus? Well, research shows or has suggested that novice individuals who do a 1RM on back squat only activate about 70% of that target muscle. So the answer is no if you're just a novice or an intermediate lifter, that no, you don't have the ability to recruit every single muscle fiber that you possess. Like it said, it only shows about 70% of the entire muscle being active in a maximal attempt in a novice lifter. But if you're more experienced, if you think maybe you're not novice, you're not intermediate, you're a little bit higher caliber, then you're probably activating more than 70, closer 80, 90%, depending on how trained you are. Second question, we're looking at asynchronous versus synchronous recruitment. Which activities or sports do you think uses each type of recruitment? Asynchronous, we know that word itself means not all at once. So if it means not all at once, then it means these are fibers taking turns. Say hi.
Hi.
Hi. These are fibers that are taking turns. And so if you're taking turns being active, think about when that would be necessary. Talking to my class. It might be necessary during an aerobic endurance event, such as cycling, running long distances, where those type 1 fibers can take turns being active. This helps to delay fatigue over time. Then we have synchronous recruitment. When would that be necessary? We would want this to happen during some sort of powerful activity. It's okay. It's okay. During some sort of powerful activity. So such as we're doing an explosive movement, such as doing a power clean or doing some like a sprint where we want all of our muscle fibers to be active all together at once to give us that explosive burst. So that's when synchronous recruitment would be necessary or beneficial. All right, so continuing on, how can we produce the most amount of force? The ability to produce force is usually controlled by two things. Number one, motor unit recruitment. How many motor units can we recruit from smallest to largest as we go through the entire motor unit corridor within our muscles, activating those? The more we activate, the more force we can produce. So that's easy. We've kind of talked about that before. The second one you've probably heard of, but it may be a little bit of a new concept to you, is manipulation of firing rate. So we have motor units that fire, right? And what this firing is basically how quickly are they able to continue their firing once they're recruited, or over time, how can they hold on to that force producing ability? Firing rate, motor unit firing rates manipulated for controlled force. And this is what we call rate coding. So if we can rate code the muscle, we are more likely to have sustained or continued force output over time. So neurons have the ability to vary the rate at generating those action potentials. We're going to look at a kind of diagram in just a second, and that'll help us understand it a little bit more. But another question I have for you is, what is neural drive? When we use this term neural drive, we are, sorry, we're talking about, or a way to say it in like a statement is, man, this at, you have to be quiet. this athlete has really high neural drive to the muscle, submaximal neural drive or maximal neural drive. So what this means is basically just they are able to activate all of their muscles and produce a lot of force during a certain event. So it's the combined motor unit recruitment and manipulation of firing rate. So write that down, at those two together. So what's neural drive? It's motor unit recruitment and firing rate. Okay. All right. So I'm actually going to skip this slide right here. So it's better to talk about it in person. And obviously I'm a little distracted right now. So don't worry about this slide. We're not going to spend much time on it, but I do want to talk about this one. So this slide is where I want to explain firing rate to you. So what we have is the neuron, the muscle fibers, and then over here in the graph, you can see force production. So what we have first is this nerve, this neuron. So as you see it slide down. Yeah, honey.
You're not at school.
No, I'm not at school, but I have to record for school because there's no school tomorrow. All right, so what you just saw is you saw the action potential arriving at the muscle, activating the muscle 2 separate times, but there was extended time between those 2 action potential stimulus. And if you look at the graph, there was force produced, but there was so much time in between that that force did not have time to summate or build on top of it. And so it just produced another small amount of force, but there was no summation. Now let's look at the second one. Look how quickly the nerve is sending that impulse. That is manipulating firing rate. It's okay. That's rate coding. And so look at the graph now. So there's little evidence of relaxation within the muscle fibers because the action potential is arriving so quickly that there's no time for relaxation. And so with this, we're building on top of every single force that's being, I guess, small amount of force being produced within those fibers, and that's the summation, which you can also talk about wave summation in a sense, but wave summation looks a little bit different than this. But this is kind of building up to like a tectonic force inside the muscle. But again, like I said, this is an example of manipulating the firing rate or rate coding. All right, so that was kind of a summary on motor units. As we move into our lectures this coming week with adaptations, we're going to talk a lot more about motor units, but I know you already know. So let's go into our last topic, which is EMG. So electromyography is the way that we measure force production in the muscle. And so the importance of this is we're going to talk about research studies that talk about how the rectus femoris was really active during this type of back squat compared to this type. And how did they know that? Well, they did a study involving EMG. So we know what it does. It measures the electrical activity of that neural stimulation within the muscle. So what we see right here are what we call contraction burst. So what I want you to do is pick a muscle in your body. I think if you're sitting down, it's easy to contract like your gastroc, or you can extend your leg, contract your quadricep muscle. So contract one of your muscles and contract and then release, contract, release, contract, release. Okay, so I just did my quadricep and I felt that contraction each time. But if you look at those signals, the signal of contraction of the same muscle within milliseconds, within a second, no, it's just a camera. The contraction bursts look different, right? So they look a little bit different because there's actually a different group of motor units being activated different times. I mean, I'm sure some of the same motor units were active, but it switches, especially with submaximal force production. And so what we pick up, what the EMG signal picks up is basically just the action potentials that are sliding across the sarcolemma of the muscle that you're contracting. And so that's what surface EMG does. And so this is raw surface recording of the rectus femoris across milliseconds. So there are 2 types of EMG, intermuscular, which uses that needle or fine wire to insert inside the muscle belly. So this will pick up very deep motor unit action potentials. Unlike surface EMG, which we're just putting those electrodes across the top of the skin, which, like I said, picks up those action potentials that just slide across the surface. Our department, kinesiology studies, don't usually use the needle or fine wire, that intermuscular EMG. That's for like nerve conduction studies or looking at like disease progression, like neuromuscular diseases. We look at it to usually analyze like locomotion or any type of movement, so kinesiological type assessments. function, coordination of muscles that are contracting during some sort of lift. So what does EMG assess? Assesses muscle activation, but that's all it really does at first, is once we get this raw EMG recording, it basically just says the muscle was active. We usually have to compare it to some other type of data, like temporal data, kinematic data, kinetic data, something else to basically get an understanding of what this EMG recording actually says. And so one thing we do know is that when the EMG signal gets larger, as it increases over time, usually indicative of higher force production. So you can see this relationship here between EMG and percent of MVC, maximum voluntary contraction, so measure of force. Why though? Why does this greater signal equal more force? Number one, more recruitment. As the signal gets larger, we're picking up more motor unit action potentials. And so that means we have more motor units being recruited, and larger motor units, those type 2 motor units, produce a larger action potential. They produce larger signals. Next is firing rate. So once we've recruited and activated these motor units, we have to keep them active, especially smaller motor units. So with our smaller motor units, I'm almost done. With our smaller motor units, they rely more on firing rate and rate coding than our larger ones do. Synchronization of motor units is another one. We want our motor units to be active all together. Hey, give me 1 second. Almost.
To be done.
5 minutes.
5 minutes done.
We want our motor units to be active at the same time, mainly for explosive events, so power, because synchronization of motor units is a better indication of how powerful you are, because it increases the likelihood that multiple motor units are active together, which decreases the time it takes to reach peak force, which means you produce force faster, which means you're more powerful. So we see that third bullet point more so in like power activities, really fast contractions, rather than slow, large force producing movements. Last is GTO inhibition. If we can inhibit the action of the GTO, it allows the muscle to be more active during that movement. And then last, we can assess muscle fatigue. So we can tell when a muscle is becoming exhausted during some sort of fatiguing protocol. So basically looking at that frequency of EMG signal decreases in muscle fiber contraction velocity due to a few things. So first, when doing a fatiguing study, we actually see the signal get larger before it gets smaller. So with that larger signal, when a person is fatigued, what do you think that means? Basically just means their muscles are having to work harder to maintain that same level of force that they were able to maintain earlier. So those motor units got tired in the beginning, and so now they're having to recruit more and more to maintain just the same level of force. And so that's why the signal will get larger first as someone is becoming more fatigued. And then if you look at the end of this picture over here, you see the signals start to drop. So one theory is motor unit dropout. They just let go of being active. They just stop. So firing rate drops. The signal to activate the motor neuron or to activate the motor unit, it ceases to exist. It just stops. We call this like nervous system stripping. So the stripping of the nervous system, the central fatigue over time, that firing rate just slows down and then signals stop arriving. And then next is molecular fatigue. So molecular, cellular fatigue, the stretch or the wearing out of the, what am I trying to say? The stretch shortening cycle, the wearing out of that stretch shortening cycle. And so when a muscle is contracting, that eccentric concentric phase, or just holding on concentrically like an isometric contraction, that is the actin myosin cross bridging process still gets fatigued. It still wears out. And so wearing out over time basically happens. And so that's that molecular fatigue. You can also add a few other things to that type of fatigue, such as buildup of acidity, hydrogen ions, lactates increasing, lack of oxygen in the muscle, depending on if it's an aerobic or an anaerobic or aerobic process. And then several other metabolites that kind of start to break down the muscle as it's working over time. But yeah, that's basically it for this lecture. So Thank you for tuning in, and we will do another one later. Okay, Braxton, say bye. Bye.